Okay, thank you. I hope you had time to grab some coffee. Sorry if the queue was a little bit long. Thank you for coming back. So this second section is going to be a bit of a focus on aquatic species. So we've seen recent dramatic changes in legislation in the UK that we now have a Sentience Act, which actually acknowledges that some aquatic species which were previously out with our animal welfare legislation are now acknowledged as sentient and deserving at least of ministers paying all due regard to their welfare. And that change is in no small part due to the work of Professor Bob Elwood, who has done some really fundamental work looking at whether or not decapods feel pain. So it's my absolute pleasure to welcome Bob to give our second plenary of the day, asking the question, do decapods feel pain? So Bob, welcome.
Oh, thank you, and good morning. This is a pure science talk that really doesn't end up anywhere with a positive conclusion, but never mind. If we think of human pain, we can generally regard two components. First, there's nociception. That is, we have nociceptors that detect tissue damage and send that information to the central nervous system. Secondly, we have the component that we actually think of as pain, and that's the unpleasant feeling, the emotion that's generated in the central nervous system. But nociception also has a second aspect. It enables a reflex response so that the animal or the human can withdraw either all or part of the body from the stimulus and thus avoid further damage. This is a rapid reflex response. If we think of damage to the finger, there is a reflex arc that goes to the spinal cord and then back immediately to the muscle so the hand can be withdrawn. There is a slower response where the message goes across to the other side of the spinal cord and goes up to the brain where the pain feeling is generated. But the thing that I want you to note here is that the fibers on the reflex are faster transmitting than are the fibers going to the brain, so that the reflex can at least be initiated before any impulses get to the brain, so before pain kicks in. You do not withdraw your hand because of pain, you withdraw it in the absence of pain. Indeed, there are some unfortunate people who have particular brain damage, and the centers that are related to pain in the brain are put out of action. But they will still show a reflex response, but they are generally unaware of it. So let's think of this reflex response. It has the effect of withdrawing part or all of the animal or human and thus stops any tissue damage, any further tissue damage. So it's an essential component in the well-being of animals. Then what then is the point of pain? Why feel bad about it if you can just withdraw without having pain? And the only reasonable answer that I keep finding in the literature is that pain changes future behavior. Because it's so unpleasant, because it's a very high motivation, it enables animals to avoid tissue damage in the future. So that is the fitness aspect of pain. Well, it was claimed about crustaceans, and in fact still is by some, that they couldn't experience pain because their responses to noxious stimuli were by pure reflex. So there was no need to be concerned about their welfare or any possibility of suffering. They were just reflex animals. So I was asked many years ago by a well-known chef did they feel pain, which at the time I thought was a silly question because I didn't think I could get an answer, and I haven't. But I looked at the literature then, and things were quite clear in the literature. These animals did not experience pain. They operated by reflex. I couldn't ask them, did they experience pain in any way? There's unfortunately no painometer. You can't stick something in an animal and measure pain. It's quite frustrating. Scientists like to do things like that. So I concentrated on reflexes and asked, well, if they're supposed to act just by reflex, can I inquire whether their responses are reflexes or whether they're too long-lasting or show signs of not being a pure reflex? And I concentrated on long-term changes in motivation that might enhance fitness, and also some short-term changes in behaviour that might appear at first sight to be a reflex, but to ask, is a decision-making process involved in that behaviour, which would imply it isn't a reflex. And I'm going to look at 6 criteria, well, I'm probably going to mention 1 or 2 more, but 6 main criteria that have been investigated, not all by me, and go through those one by one. So first of all, avoidance learning. A key aspect of pain is to avoid future tissue damage, so we would expect rapid learning. And I mean rapid learning. There's no point in taking 100 trials to learn something if you're trying to avoid tissue damage. You know, there'll be nothing left of you by the time you've learnt the response. So we're looking here at rapid learning, and I use shore crabs as the example of the species. And shore crabs I chose because they are found under rocks at low tide in daylight. If they come out, they tend to be snapped up by seagulls, so they do tend to avoid light whilst out of water. And the aim was to plonk them in the middle of a brightly lit chamber in which there were 2 simulated rocks, one on either side of the chamber, and they could go to one or the other. And I placed them, or we placed them repeatedly in this situation. Every 2 minutes the animal was taken out and put in the centre and said, take your choice. And in one of those shelters, the animal would receive a shock every 5 or so seconds, as long as it stayed in the shelter. In the other shelter, it was quite safe. And the shock was delivered by fixing insulated wires with the insulation removed, and then that part of the wire was wound around the base of the hind walking legs where there is no calcareous covering. Crabs were randomly selected to receive a shock or not in the first chosen shelter. So, and if that shelter was chosen on subsequent trials, if they received shock, the shocks were repeated, but no shocks given in the alternative shelter, and there were 10 trials. So the question is, in the first trial, some were shocked, some didn't receive shocks, and we're asking what happened, how did that affect their behaviour in the second trial? Did they stick with their first choice of shelter, or did they switch to the alternative shelter? And we can see that the shock or not had no association with their choice in the second trial. The shock did not affect their behaviour in that respect. Rather, what we see is there is a significant tendency to go back to the original shelter. Perhaps they don't know about the alternative shelter, they might not be aware of it, but whatever it is, they are showing a strong preference for the shelter that they chose the first time round. Okay, so let's look now what happened in the third trial, dependent upon their choices in the second trial. So some were shocked, some were not shocked, some stuck with their with their previous choice in trial 3, some switch. But now you can see that there is an association between the behavior and whether they were shocked or not. Far more of those crabs that were shocked now switched to the alternative shelter. So the shock was having an effect on after 2 trials. That response continued, and we found that over the 10 trials, more crabs tended to use the non-shock shelter compared to those using the shock shelter. And then there were some crabs which stopped using shelters. They refused to enter a shelter. During the trials, we saw that some crabs got out of the shelter. That never happened if there was no shock given in the shelter. But over 50% of the crabs in each trial got out of the shelter, and that number increased over the trial. So these animals are not only learning not to enter a shelter, to switch shelters, they're learning to get out, and they were getting out more likely and more quickly as the trials went on. So there seemed to be a different aspect of learning. So we conclude that shore crabs showed evidence of swift avoidance learning. This is not predicted by a nociceptive reflex, and the data are consistent with the idea of pain. That's my favourite phrase. It doesn't mean that I've shown pain. It means that the data are consistent with pain. So let's look at motivational trade-offs, and it's a rather different approach. If we think of behavioural decisions, then there's usually involves some sort of trade-off between different requirements. We all require different things. Do I require a drink? Do I require food? Which shall I do? How hungry am I will depend on how much water I take. Whereas reflexes don't require any of that. It's just going to happen or not. Doesn't matter what else is going on in the animal's life. And we can see that clearly in zebra. These zebra, they've been walking on the plains for maybe a day. They've come to a water hole and they drink almost immediately, but we can see that that drinking isn't a reflex response, because these zebra have come to a water hole, but they're not drinking. They are trading off a requirement for water with predator avoidance. So we can see that that is a behavioural decision. And we sort of looked at things like this with hermit crabs. Hermit crabs are those decapods that live in empty gastropod shells, and we wired up shells so that we could put the naked part of the wire just on the inside of the shell so that we could shock the crab on the naked abdomen. So there's no calcareous covering at that point to impede the shock. And we could ask, does the crab get out of the shell? And does anything influence whether the crab gets out of the shell after being shot? And is that then a reflex response? And in one experiment we did, we looked at a trade-off, rather like the zebra, but in shells. We compared crabs exposed to predator or non-predator odour when shot, and some crabs were exposed to an odour of shore crabs, some were exposed to mussel odour, non-predator, and some just had seawater. And we can see that with seawater or a non-predator, the vast majority of crabs got out of the shell at the shocks we delivered, whereas with predators that was markedly reduced, only 41% got out of the shell, and that is a significant difference to both the control groups. So clearly then, that is a trade-off between avoiding predation and avoiding the shock. It's not a reflex. Getting out isn't a reflex. It's a behavioural decision. And we got a similar result in an experiment that wasn't designed to show anything about trade-offs. What we did was to use shell preference. I've done a lot of work in my lab on hermit crab behaviour, how they fight, and about shell preference. It's all about getting just the right shell. And on the shores of Northern Ireland and much of the British Isles, small crabs are found in two main species of shell. They're found in these littorina shells, which they really, really like. And they can be found in these gibular shells, which they really don't like. Give them a choice, they'll take the preferred shell, the littorina shells. We can think of these as lovely littorina or grim gibular. So, and here we have a picture of a fight just starting. This crab in the unpreferred shell is going to try and beat up this crab and get it out of the shell and take its shell. So what we did was to induce crabs to occupy either good quality littorina shells or poor quality gibular shells that were wired up. And we delivered shocks to the abdomen of those crabs for some of the crabs, not all of them, but half got shocks, half did not get shocks. And some of the crabs got out of the shells, and then most of them moved back in subsequently. What we did was, shortly after they got back into the shell, if they got out, we offered them a new shell. And that was the aim of the experiment. The experiment was aimed to ask about the motivation towards the new shell, not about whether they got out or not. And we were actually aiming for them not to get out. We were delivering a shock at a level just below that which we thought crabs would get out of the shell. But of course, crabs being crabs, some of them got out. But when we looked at the data, you can see that only 12% got out of the lovely littorina shells, but 36% got out of the grim gibular shells, and that was a significant association there on the Fisher exact test. And that demonstrated a trade-off between avoiding the shock and keeping a good quality shell. Well, as I said, the aim was of that experiment, although it showed nicely a trade-off, the aim was to look at long-term changes in behavior to see whether the motivation towards shells changes over time. And those offered shells after a shock reacted differently to those that had not been shocked. They were more likely to approach and more likely to move in to that new offered shell. And if we look at the latency to approach, crabs that didn't get shocked took longer to approach the new shell than if they were shocked, didn't matter what species. And they investigated the new shell much more quickly. Crabs that are investigating an empty shell typically feel into the interior. They probe their chilipeds or claws into the interior of the shell and investigate that way. Crabs that were shocked had far fewer probes with the chilipeds. They were much more highly motivated to move into a new shell having been shocked. But again, the noxious stimulus is having a long-term effect on the animal, and that happened even after 24 hours between shock and offering of the shell. So let's look at prolonged directed rubbing. We used prawns for this. One antenna was pre-treated with either water or anesthetic. Whilst out of the water, it was put back into the water. We observed the behavior for 5 minutes, then took it out, and we then treated that same antenna with water or sodium hydroxide or acetic acid, or it was pinched with forceps. And looking at grooming, they showed two responses that were worth mentioning. Grooming the antenna, where they pulled it repeatedly through their little claws, or they rubbed the antenna against the side of the tank. And what we see is that two treatments with water had no effect on grooming. Pinching seemed to have very little or no effect. But the two chemical treatments had a strong effect on grooming and indeed on rubbing against the side of the tank. If we look at what they were doing with the alternative antenna, That didn't happen with the alternative antenna. They were somehow apparently aware, or could at least localize which antenna had been treated. And if we looked at the effect of a local anesthetic being applied in the pre-treatment, we could see that reduced the amount of grooming and rubbing. I'm not showing those data. We see activities directed towards the site of a wound or noxious stimulus in other situations, so that those hermit crabs that got out of the shells having been shot frequently groomed their abdomen, just where the shot would have been. They attended to that point. We've never seen that. We remove a lot of crabs from shells in my lab over the years. It's an industrial practice. And we have never seen a crab groom its antenna unless it had been shot. We saw guarding of wounds in edible brown crabs where they had a claw removed in the style that fishermen use, then they guard and tend to the wound. So those activities are all consistent with the idea of pain. Well, let's look at anxiety. This is some work done in Bordeaux, and very nice experiment. If you put crayfish into a cross maze which has 2 dark arms and 2 light arms, if you plonk them in here, they wander through all the arms, showing a slight preference for the dark, but it's only a slight preference for the dark. However, if you previously put them into a chamber in which they receive a shock, receive repeated shocks, then put them into a cross maze, they now wander backwards and forwards through the dark areas and avoid the light areas quite markedly. And here's a distribution of use of the light areas for unshot crabs, and these are for shot crabs. You can see there's a marked shift in that distribution. These workers, Fawcett and his co-workers, looked at serotonin levels both in the hemosyl and in the brain, and found higher levels of serotonin in the brain if the animals had received shock. So they then asked, did serotonin have an effect on the behavior of these animals? They injected some with serotonin, some without serotonin, just saline, and then put them in the maze, and they found that those injected with serotonin now behaved as if they'd been shot. They hadn't been shot, they just had serotonin. And they described this as anxiety, as a typical risk avoidance for crayfish. Being in the dark is better than being in the light. It's a risk avoidance behavior. And remarkably, an experiment that I found quite surprising is that there is an anxiolytic treatment for humans, Librium, for people who show abnormally high levels of anxiety. And if you put crayfish in without being stressed, they show this behavior. If they're stressed, you show this behavior. If they're stressed and you have Librium, this inhibitor, this anti-anxiolytic drug, they now behave as if they hadn't received the electric shock. So Librium works on crayfish as well as on human beings. We also see changes in physiology of the animals. We've seen that with serotonin in that crayfish experiment. Crustaceans have a stress hormone called the crustacean hyperglycemic hormone. It acts in the same way really as cortisol. It's not cortisol, but it has the same main action. That is to use the glycogen stores in the animal and to convert them to glucose. And so glycogen is split into glucose and pyruvate, and then lactate will increase because of that reaction. In some fisheries, the claws of crabs are removed. and the live animal is then thrown back into the sea. We did some experiments in 2007 which looked at changes in glucose levels for those that had had one claw removed. In fishery practices, both are removed. If one claw was removed by fishery practice or they were just handled, and we see a marked increase in glucose. There is an increase in lactate, a very rapid increase in lactate. We couldn't measure, or there were no differences in measurement of glycogen, but the glucose to glycogen ratio shot up dramatically in those that had a claw removed. When you do things like shocking an animal, of course, you tend to make the animal rather active. And when you find a shift in lactate, it's always possible that is due to the increased activity in the animal rather than the shock per se. So we ran this experiment on shore crabs, shocking some and not shocking others, and then to try to standardize the crabs on the basis of their behavior. And quite a few crabs that were shocked just walked around. Some showed extreme behaviors such as threat responses or trying to climb out of the enclosure. We took those out of the data set. And on those that weren't shocked, quite a lot of those walked around and some didn't walk around. We excluded those that didn't walk around. So we just had crabs that walked around, but some had been shocked and some hadn't been shocked. And what we see is hugely increased lactate levels from those animals that were shocked, and that is irrespective of their behavior. So we can see that shock per se has a physiological stress. So what we see then is that these data on crustaceans go beyond simple nociceptive reflex. There's a long-term motivational change after exposure to noxious stimuli, and behavioral and physiological data are consistent with the idea of pain. There's some sort of awareness of the site of injury. Hermit crabs leaving their shells and shore crabs leaving their dark shelters mean that they give up valuable resources. They pay to avoid the shock. There are indications of anxiety. There are indications of increased attention to danger and increased fitness. I haven't had a chance to cover those in the talk, but there are good data on increased fitness due to the messages about damage getting into the central nervous system. However, all these experiments do not prove pain. Certainly no one of those experiments proves pain, and even together they don't prove pain. But nevertheless, we're now at the stage where there's an accumulation of evidence, and that suggests that we cannot dismiss the idea of pain in these animals. Thus, I say we should give these animals the benefit of the doubt. We should apply the precautionary principle so that they are slaughtered in a humane manner. And just to look over a recent history, I was quite taken aback when the first of these studies was published in the amount of media attention. It was ridiculous, and I got to the stage where I told my university media office, I am doing no more interviews, just forget it. I can't take it anymore. They still came back once. It was Children's News, BBC Children's News wanted to do an interview with me, and the media office begged and said, we've never had a request from Children's News. So I thought, well, if my work is suitable for children, then perhaps I've achieved something. There was a shift in attention on various adoption of ideas. Switzerland, a couple of years ago, 3 years ago, changed the law to ban the boiling of live lobsters. The British Veterinary Association took the stance that they demanded humane slaughtering of these animals. The RSPCA came on board. DEFRA commissioned a highly influential and important report on sentience in cephalopods and decapods, and came to the conclusion that they should be regarded as sentient, and that bill was passed in Parliament. So there has been a remarkable change, and I'm not quite sure how to regard that. It was never my intention. I was just a simple scientist, and I wanted to answer a question that I was asked in a pub. Do these animals feel pain? And somewhat frustratingly, I can say that after about 17 or 18 years research, I come up with the idea of possibly, probably. And normally I go for a stronger answer than that, but never mind. At least we got somewhere. So I'm going to say thank you and stop at that point.
Thank you, Bob. I think you're underplaying the influence that your work had, and it's clear that people made their own conclusions, and I think it's great to see the precautionary principle in action in that case. Questions from the audience? Anywhere? I had a quick one before we go to that one at the back that I could see, which was, am I right in thinking when you were showing me that prawn data that they're not responsive to mechanical pain or mechanical noxious stimulation? And if not, why would that be, do you think?
That's a good question, and one which we pondered. Pinching the antenna the way we did it, with, which was not right at the tip, but it had very, very little effect. There was a tiny increase on rubbing, but not on grooming, if I recall. So there was some effect, but it was minimal. But if you do a much more dramatic tissue damage that we have done with trying to simulate the fishery practice of removing claws, that does have a very dramatic effect.
There was one
yeah.
There are a couple of
Awolf Seni from AHDB. Is there any indication or an estimation of the time from the experience of a noxious stimulus to the time it is processed in the brain? So from experience of the stimulus to the time it's processed in the brain.
I don't have an answer to that question because you've not investigated the actual impulses getting to the brain. But with dramatic tissue damage, we noted a shift in lactate within 1 minute of the tissue damage. And I'm assuming that the brain was involved somewhere in that. I would imagine that the impulses get to the brain, but this is my imagination, in a second or less, as fast as nerves can carry impulses. But we've not measured it.
There's one at the front here. Oh, sorry, sorry.
Thank you for this very interesting talk. I was wondering, do you know anything about the regenerative capacity in crustaceans? Because in fish it is way better compared to human beings, so it is possible that long-lasting pain may have a bigger impact in human beings than fish. So that's why I'm wondering, what do you know about this in crustaceans?
There was a key word you used about the 5 words in, and I missed it. Was it regenerative or?
Yeah, regenerative, yes.
Do they regenerate behaviorally or?
In terms of tissue damage. Can
in terms of damage?
Damage
Okay.
tissue quickly? I don't know, that's why I asked.
When you ask fisheries about taking claws off of crabs, they will say that is not a problem, that's a sustainable harvest, because crabs will regenerate claws, and they do so at molt, and it's small crabs that molt frequently. But the crabs that are harvested, the claws that are harvested, are from large crabs, which basically have stopped growing. So they don't regenerate their claws, and in fact there's a very high mortality within an hour or so of taking 2 claws off. The animals are likely to die, and those that survive are likely to die of starvation.
Okay, thank you.
Steve, there's one up the front here.
Hi, Bob. I'm Eva from the LSE. I was wondering, is your answer to the question of does X feel pain different for any other groups of animals, maybe mammals or maybe just humans? Like, would your answer be yes rather than probably? And if so, what's relevantly different?
Well, you're asking that impossible question.
I'm sorry.
What does the animal feel? I don't know. I know what I feel if I hit my finger with a hammer. I can see that you would behave and do all sorts of things that I might do if you hit your finger with a hammer, but I'm not sure whether you're feeling exactly what I feel. So it becomes a pointless question. It's bound to be different. But what we can say is that pain is a motivational state, similar in some ways to thirst or hunger. It's a motivational state. It's one that animals seek to avoid. It's one that we seek to avoid. We can show that these decapods have that motivational state. It changes their behavior. They pay to avoid these things. They learn to avoid these things very rapidly. And so they do all the things that if you think, well, I'm going to define pain as a change in behavior, then if you do that, you can say, yes, they have pain. But as soon as you phrase the question as, do they feel pain, it becomes a slightly different question, and you can't help but reflect on your own feeling, and that's where you start, and that's where you lose the answer, I'm afraid.
So, can I sort of follow that one up and ask you to be more specific? Would you be more or less certain about mammals than you are about crustaceans, for instance? I suppose that's what we're curious about.
Yeah, mammals, they're more persuasive. We feel a greater affinity to mammals. We have them as pets. They vocalize. And if you ask the general public about pain, they home in on this vocalization. And so there is this fascination with the myth of lobsters screaming when they go into hot water. Because people who are firm believers in animal welfare actually want that sign as a sign of pain. Of course, lobsters don't have vocal cords, they can't scream, and they're not vocalizing, and that loses some of the appeal for people, I think. But then why? I mean, it's illogical to say, well, if these animals have no vocalizing ability, why do we suggest that they really should vocalize if they're feeling pain? It's a bit like saying, well, if you do something nasty to a bird, it'll fly away, unless it's an ostrich, so ostriches can't feel pain, they don't fly away.
Yeah. Fantastic, thank you. Were there other questions in the audience? I can see, yeah, one over there.
It's Graziano Fiorito from Naples, Stazione Zoologica, and I have a question whether in avoidance learning you have any knowledge about differences among species in terms of memory traits, because it will be very interesting, I think, to see I'm saying if there, you know that there is any difference in memory trace in avoidance learning among different species of crustaceans.
Is there a difference in the brain?
No, in memory trace, in memory recall. Yeah.
I've done a huge comparison between manual learning and the speed of learning is remarkable. And there's one recent study in Japan using crayfish that has shown an effect of being shot after just one trial. They would shift their behaviour after just one trial. In that case, they didn't have the crayfish having a preference of doing one thing and then having to shift. In our travel experiment, they had developed a preference for one particular enclosure, and so they had to overcome that preference to shift to another, rather than simple straightforward learning which one to go to. But they learn remarkably quickly, and I would say as quickly as mammals.
Fantastic. I think we should move on to the next talk there, but thank you so much, Bob. That was absolutely fascinating. Thank you. So next up, we're going to move on to other species that have recently had their sentience, at least in the UK, formally acknowledged. And I'm delighted to welcome Giovanna Ponte from the Association for Cephalopod Research in Italy, talking about bringing humane slaughter to cephalopod molluscs. Welcome, Giovanna.
Hi, good morning to everyone. I'm very happy to be here to present our activities in trying to bring human slaughtering to cephalopod mollusk. So our aim is to try to develop an efficient human slaughter method for different cephalopod species, and in trying to test and assess two different methods of stunning cephalopods, mechanically and electrical stunning, adopting the ESPA eligibility criteria. But what we are talking about? We are talking about cephalopods. Cephalopods are very different group of animals. They are adapting in different environments, and all of them require and they need specific care and welfare differently from each other. We are talking about more than 800 species, starting from nautilus, so we can see cuttlefish here, octopus, very small squid like Euprimna, or very huge, even if this picture is a fake picture that you can find on the web. So, but they are living in all the ocean around the world at different temperature, even very low temperature, all depths, and from benthic and pelagic habitats. So they are widely studied around the world, different species of course, spanning from neurobiology, genetic, robotics, engineering, artificial intelligence, and even arts and other disciplines. So, but I want to underline the relationship between these animals with humans. So if you, for example, in arts or in music, search for octopus word, you can find more than over 108 lyrics. But even in the social media nowadays, you can see that cephalopods receive more interaction in comparison with fish or other marine mammals. With this aspect, I cannot avoid to cite, of course, the film documentary that won the Oscar last year, My Octopus Teacher, and the strong relationship between the octopus and humans. But on the other hand, we have these animals that are included, all the live cephalopods in the Directive for Protection of Animals, and I have to say that we have in this directive more than 800 species, and the directive cover both adult and juveniles, not eggs. So this means all the live cephalopods. So, but on the other hand, again, cephalopods are used for as food, and they represent almost 4% of the total volume of fishery around the world. So this is an example as a salad, and if we compare these species, for example, the squid for the consumption for pro capita or a 3 years trend, the squids are reported here in orange compared with mustard and shrimps, you see that we are still low. So even if we compare with the aquaculture volume in Europe, we see that the unit utilized between cephalopods and salmon, for example, is totally different. We are talking about kilograms versus tons. Even if in the last years, thanks to the on-growing factories in Spain, where they are making some octopus, they still start to be higher. So, but if we look at the Mediterranean countries for the top 10 products in import and export, we see that octopus, squid, cuttlefish are always present between Italy, Spain, Greece, we said already, and Morocco. So this means that there is a sort of very interest for this kind of animals as food, and this is mainly, I can say that for the healthy, safe food, they are considered very healthy with low fat presence and are less affected by environmental pollutions. This is also reported with a member of our group of our team project with Ole Morrison, that is a promise for the future. But what is the main issue and problem with these animals? The main problem is that at the moment, the way of capture of this animal is very scarce, and they use different approach that are not, let's say, humanly correct. And they use mainly, as you see from these examples, these tables here for Portugal, troll or multipurpose seine. But this is also in relation with the size of the vessels. You see here the 61 vessels, that is only the 4% that are using tools because they need a huge boat, differently from the multipurpose where we reach a higher percentage. So this is a sort of very short movie that I will try to short, where you can see an example of the fishermen of octopus in Portugal. They release in the water nets and traps, and after 12 hours, they are starting to collect animals on the boat, and on how they manage and take, they are not taking care of these animals, because they are just removing animals that are still alive, putting all together in a bowls or even in a solution of seawater mixed with the ice tap water without taking account any kind of care. So apart from this, okay. So I want to underline that there is no evidence, at least at the moment, for specific and systematic slaughter practice for this species. So this is why our main aim and involvement is also with policy. So we are working on with FELASA for recommendation for capture and transport of cephalopods for scientific purposes. What we are doing is producing a review paper, more than 100 pages, and the FELASA WG report, analyzing the scientific literature with more than 300 papers, the best practice utilized, and then try to identify what is missing or required. So in this report, we identified the best, most recommended in green and yellow, the second most recommended capture method for different species of cephalopods. You see here Nautilus, that is different from squid or octopus, for example, or even the best transport method that can be utilized for these different species as an example. So In addition to this, what we are doing is to propose for a training program that should be free for fishermen and a protocol for testing the effect on animal welfare of this animal. This is with the aim of increase our chance and with the interaction with the fishermen communities and to provide guidance and training and to facilitate collaborative attitude among different stakeholders. In addition to this, what we are doing, and this is in press, is informing the European Commission about the mandata minima requirements that should be included for the housing and care of cephalopods in the revision of the Annex 3. And these mandata minima include a list of welfare table and parameters, as you see here, for different species, considering more than 250 references and including also a sort of table for different species of the minimum requirement for these animals in laboratory condition. In addition to this, we are also working on the recommendation for humane methods of killing of these animals that will be included in the Annex 4. This is our effort, let's say, with the policy to facilitate and contribute to the European policies, but also worldwide. On the other side, of course, we are running some research. The first one is to develop and implement the welfare index for this animal, considering the welfare triangle, considering physiological, physical, and psychological, let's say, welfare indicators in trying to identify what are the physiological needs for this animal as temperature, oxygen, stocking density, and etc., and trying to develop some methods for assessing the welfare of this animal not invasively. This is an example of the corticosteroid level of these animals, and this is a comparison between feces and mucus in order to try to find a non-invasive approach. On the side of this, also measuring some physiological parameters, for example, here is an heart, you see here, for trying to image the cardiac input and output of these animals in different conditions, normal conditions here, or with under anesthesia with a more slow motion of the heart. But this allows us also to identify and assess the heart rate on the left here, or the respiration rate of these animals, and in different conditions, as I said before, to monitor, even during the anesthesia, the physiological aspect of these animals before anesthesia, during anesthesia, and the recovery. But with this technique, what we are doing is also to try to identify and some mechanical stunning in order to, let's say, stunning these animals. In this example, what we are doing in try to develop an air stunning compressor air prototype. In these trials, we fixed at 6-8 bars. And after this, we are trying to identify with the electrophysiological recordings the activities at the central nervous system. But apart from the mechanical stunning that we are, as preliminary results, we got some, let's say, what we can say that this the conclusive captive bold is not good for this type of animals because of some feature of the cephalopod school, and the percussive seems not enough as a single shot, but seems to be good for as a multiple with a train of 3 shots of 8 bars for 3 seconds. In parallel, what we are trying to do and in trying to develop what is the electrical stunning, we are trying to measure the impedance of these animals as an indication of the optimal electrical frequency to be utilized for electrical stunning. So our preliminary results show that it's very similar between cuttlefish, the first 2 species as trial, and octopus. And what we are trying to do is and we have to ameliorate this aspect, is then utilize these hertz for using in this electrical stunning. We start with the cuttlefish with this part of research, putting the electrode in correspondence of the brain of these animals, but we see here that in contact with the cattle bone tip, and in these examples you see here that there are some burnings that are present on the skin in correspondence of the eye of the animals, arms, and cattle bone tip here. In this case, with this position of the electrode, the 50% of animals recovered putting in seawater. On the other hand, in putting the electrode under the cattle bone that is more close to the brain, we saw that there is little burning just evident around the eyes and in corresponding to the head of the animals. In this case, putting the animals for 30 minutes in seawater, they never recovered after stunning. So this is our preliminary, let's say, results using 50 hertz with these animals. But of course, in parallel, what we are trying to do is also to find a non-invasive approach with electrode to measure the EEG in the brain, in the pallial nerve here, or even, this is an example of one animal with 2 electrodes on the side, on the pallial nerve, to measure the activities and stimulating, as you see, some areas on the mantle, we were able to record on one side or one other, or in both sides, stimulating the middle line of these animals. And these are some shots of the activities recorded, and on the other side, but what we are trying to do is to try to record the spontaneous activities, putting an electrode on, not in the brain, but on the brain, you see, with the ultrasound machine that is here. And this is, let's say, a picture that is more close on the brain. And what we got is that putting the electrode subcutaneously, not inside the brain, but under the skull, we were able to detect a sort of activities that is a train of activities that very similar to mammals with the EEG. But pinching on the animals, we were not able to detect any kind of response. On the other side, if we move the electrode instead of the central part of the brain, more on the side, where is the brain peduncle, more close to the optic lobe, we were able to identify a peak just after the main activities of these animals. This is something that is still ongoing, and apart from this, another way that we are trying to do and to develop as a non-invasive recording of EEG in the brain of these animals is inspired by the study in humans and mammals in trying to use a non-invasive near-infrared spectroscopy. And we are doing this together with, of course, even with for the others, and this is reported developing a concept to non-invasive measure blood oxygen saturation in cephalopods. That is a thesis just a few months ago, finalized, and we were trying to build up a prototype in order to measure the oxygen in these animals. These are some technical information, but the main result is that considering the physiology of these animals, the standard transmitted based pulse oximeter is not ideal for these animals. And what we are trying to do, and this is the prototype, is a reflectance-based concept that should be useful for these kind of animals. And in this case, we can have a multiple sensor, each covering specific wavelength, because the main problem is that we don't, of course, I mean, cephalopods do not have emotion, but the hemoglobin, but they have emotion, so we are working on different wavelengths. And with this, I want to conclude. Thank you all for the attention and all the people involved in this project. Thank you.
Thank you very much. Absolutely fascinating whistle-stop tour of cephalopod welfare. Any questions from the audience? I can see one at the back there, right-hand side.
Good morning, my name is Ian Robertson, Association of Meat Inspectors. I'd like to know if there's a correlation between better handling of the live animal and a better death and the quality of the product.
Sorry, I didn't get the words, the microphone noise. So any correlation between?
Correlation between handling of the animal and the quality of the product as in the meat?
We are still, I mean, I didn't include this in the presentation because we are starting with the trial. What we are doing with another member of our project is to study the effect, apart from the handling, even of the procedures of the capture and killing of these animals, on the quality of the meat, let's say, and this is in collaboration with Ole Morutzen in Denmark at the University of Copenhagen. We just started with some trials, so we still don't have any answer for you, but we, even this part is included in our project, yes, of course.
Any others? Yeah, Jade over there, I think.
Thanks very much, Giovanna. Jade Spence from the Humane Slaughter Association. Given the unusual anatomy compared to most of the types of animals that stunning research is done on, do you anticipate that there will be a pressure where you can achieve an effective percussive stun with a single shot, or do you think it could be too difficult given the anatomy?
So the main issue for what we are trying to do, we started with sepia and octopus, but our main animals, so the starting, let's say, for trying to understand with the captive bolt is with octopus, because at least we don't have the cattle bolt. So with the single shot, we were not able to see any kind of effect, and we are able to still record sub-signal. So this is I have to say again that there are still preliminary results, but it seems, at least on the trial part of the project, that the multiple shots, as I said, 3 trials seems to be more efficient to remove any activity in the brain. Yeah. But with the ultrasound machine, we were able to see some damage on the tissue and with the recording. Yeah.
So maybe I could just briefly follow up on Jade's question. If you have to use 3 shots, do you think that's acceptable in welfare terms?
Yes, I have to say that after seeing the presentation this morning, I say that since we are just starting in this world of human slaughtering protocols for cephalopods, it can be acceptable. And then we will see if we'll be able to manage. We have to say that it's very hard because cephalopods, I didn't mention, but I think every one of you know, they do not have any kind of skeleton support, so they are molluscs. It's not easy to block them, so this is still like the research needed for trying to identify the best method. Yeah.
Exactly. So better than nothing for now.
Yes, of course. It's
fantastic. Okay, well, I think we better move on, but thank you very much. That was absolutely fascinating. Thank you. So, unfortunately, our short talk on the welfare of saltwater fish in Hong Kong is cancelled because Desiree Hung couldn't make it. So we're going to move straight on to another piece of HSA-funded work on in-water electrical stunning for slaughter of farmed finfish, and I'm delighted to welcome Professor Jimmy Turnbull.
Thanks, Hugh, and thanks to the HSA for the funding for this project. So the project on the humane slaughter of farmed finfish involves a bunch of partners, including Ace Aquatech as the lead commercial partner, universities of Stirling, Bristol and Urter in Catalonia. My name's Jimmy Turnbull and I'm doing the presentation, but there's a whole team of people involved. So, and actually Jeff Lines and Jenny Bousma are both here today. And Jeff is the expert, he's a physicist, but he's the expert on the electrical engineering side. So if there's any questions on that side, I will pass over to Jeff at the end. Just a little bit of background to start with, something about aquaculture and fish in general in terms of their consumption. Fish are the primary source of protein for well over 1 billion people, and most of these people are poor people in low-income, food deficit countries. It's also, aquaculture has been the fastest growing food production sector for more than 50 years, the only one that's grown faster than human population, up and over 500% since the 1970s. Estimates are very variable and imprecise. And these days, more than half of the fish, that's actually that's an error. It's really half of the seafood eaten by humans is now farmed. So are fish important? Well, fish isn't even a taxonomic grouping. It's an accumulation of an incredibly diverse group of animals, and with all sorts of evolutionary and behavioral backgrounds. But there are many examples of complex mental processes, and I think I'm just going to copy Bob's word. We need to give them, we have evidence that's consistent with sentience in fish, and obviously we can never, I'm just going to end up repeating his words, so I'm not going to do it. Regardless of our scientific or personal opinions, their welfare is protected by law in many countries, and one of the things that is really important to remember is the massive number of fish that are killed for human consumption every year. Some colleagues from Compassionate World Farming have been trying to put an estimate on this, and it's absolutely enormous. Tens or hundreds of billions of animals every year killed for human consumption. And the vast, vast majority of them are not stunned at all and suffer a poor and unpleasant death. The reality of this is that they are pulled out of the water in unpleasant circumstances and then left to either asphyxiate and dehydrate in the air or placed on ice and for a slow death. This is not really pleasant for the fish or for the people involved in the process. And in capture fisheries, the capture of wild fish, they may even be processed alive. I should make the point at this stage that in the UK, our major aquaculture industry is the production of Atlantic salmon and rainbow trout, and they are world leading in terms of the welfare of the animals at slaughter. All of them are now stunned pre-slaughter. The majority are probably stunned by percussive stunning, which when it works well is very effective, but it's a little bit sensitive or ineffective if there's variations in size or conformation. And there are some issues associated with machines which simultaneously concuss or deliver percussive blow and bleed the fish at the same time. In-water electrical stunning is now used widely, but is still being refined to adapt to local conditions and also to minimize carcass damage. A point that was raised by a question after the last talk: careful, low-stress handling prior to stunning and slaughter is absolutely essential. You can make a huge difference not only to the response to the whole stunning and slaughter process, but also the subsequent product quality if you don't handle them very gently prior to the slaughter process. So, I think the caption's gone off the top of that slide, but never mind. So what are we going to do to try and improve the lot of tens of billions of other fish that aren't salmon or trout? Often each harvest involves large numbers of often very small and relatively low value animals. And so the reality of the situation is that effective stunning will be most likely implemented first in the large commercial industrial scale operations. And the incentives which we have to take account of, if we're going to make a difference and get people to adopt these things, then we need to be aware of the drivers that might influence their decision making. So ease of handling, product quality, and market forces, demand for better welfare at slaughter, are the things that are going to make the difference to the producers. And our opinion is very much that we're not trying to set our sights on perfection, but we're trying to look for rapid adoption of improvements in a relatively short timescale. If we go for perfection, we're unlikely to achieve anything in the near to medium term future. So, Systems need to be high throughput because of the large number of animals, they need to be affordable, and they need to be reliable. Our opinion is that in-water electrical stunning probably provides the best option here. Percussive stunning, when it works well, it can be very effective, but it needs very careful setup, and it's not suitable for small fish, and it's not suitable for some of the main aquaculture species worldwide. The anatomy of the head renders it a relatively ineffective way of stunning them. Dry electrical stunning, there are some systems out there, and I'm not going to kind of do a comparison, but we feel there are some issues with that. For the people that are used to terrestrial animal slaughter processes, CO2 is not an option for fish. It's absolutely horrific. It's highly, highly aversive. There are some ways you can mitigate that aversion, but at the moment it's just not an option. So the aims of the project are to target the major non-salmonid farm species. We have used some salmon in order to transfer the technology that's been developed for salmon to the other species. We're trying to take on the impossible task of assessing consciousness in fish, or at least getting a decent indication of consciousness. And we're evaluating stunning systems under controlled laboratory conditions. There's another half to the project, which I'm not going to have time to talk about today, which is the development and refinement of stunning systems, evaluation of those systems in the field, and actually the deployment of pilot systems out on real slaughter facilities. So the project was designed as a research, development and deployment project. So we expect to see real changes in terms of the numbers of animals stunned prior to slaughter during the lifetime of the project. It's not research which will then start to be applied. So our grand plan was to start with what we already know in salmonids and apply that to tilapia, which in retrospect was not a great idea. Tilapia have a brain which is highly protected. This is just a diagram to demonstrate where it is in a vertical plane, and in a horizontal plane this is a dead dissected tilapia. The brain is in the middle here, and from this CT scan you can see that there's these bony ridges and this massive muscle, and then very, very dense bony scales on the top. So highly protected brain, which is unbelievably resistant to damage, and rendering percussive stunning almost completely, well, it's not ineffective, it probably gives them a very sore head, but it certainly doesn't stun them. And also very, very resistant to anoxia. And there's also a high level of inter-individual and inter-population variability, which again don't make them the best experimental subjects. So the current state of the project, well, we're not as far along as we would like to be because of COVID, and everybody knows that story. We spent a lot of time developing and refining protocols and equipment, and this is some of the experimental equipment here. When you're dealing with electrical stunning of animals, obviously there is the potential to create a great deal of suffering and harm in those animals, and therefore we're rigorously applying the principles of the 3 Rs and minimizing the number of animals for robust results. And so we've been very cautious about making sure we know what's happened with each individual animal before moving on to the next one. Some work has been conducted. This is just a diagrammatic representation here. This was done by Jeff, Jenny and Maureen, looking at the effect of the electrical field on the contraction of the muscles to try to minimize carcass damage associated with electrical stunning. And there's also been the development of commercial systems, and actually the literature on the right here refers to a tilapia stunning system which is already in place in a production facility in Mexico. Consciousness, awareness and sensibility. Well, so our idea was to try and triangulate with EEG and conventional evaluation of consciousness. So for more than 3/4 of a century, people have been assessing awareness in fish through anesthetics. So there's a clinical assessment, And the idea was to compare that with EEG. Now, I would like to just make it clear that we were not validating the behavioural things with EEG because there's no clear EEG definition of awareness or consciousness in fish. So it was a comparison of the two rather than validation. Clinical evaluation of consciousness is based on the writing reflex, movement, eye roll reflex, response to stimulation, opercular movement or breathing. We heard earlier on about evaluation of these things in terrestrial animals, in mammals and birds. These things have not really been well validated in fish, so we really don't know how consistent or reliable some of these indicators are. The question that's been raised is, when you stun them within water electrical stunning, are they paralysed or are they unconscious? And I'm going to come back to that just at the end of the talk. So initially, the plan was to use this external placement of electrodes on the surface of the fish, which had been developed for salmonids by Albin Gran's group in Gothenburg in Sweden. We were communicating regularly with Albin and his group, and both groups, the group in the UK and the group in Sweden, found that the external placement didn't work in tilapia. It does work in other species, salmonids and some catfish, but it didn't work in the tilapia because of the anatomy of the head. So we had to revert to needle electrodes. And however, because of the scales on the surface of the fish and the anatomy of the skull, the placement of the electrodes is a bit of a challenge, and getting consistency is quite a problem. So a colleague at Bristol was generous enough to do some CT scans for us so we could try to improve that placement. For the EEG, we've been looking at visual evoked responses or visual evoked potentials, where you have flashing light and then a simultaneous spike on the EEG recording, and then you record the response to that, but also a somatic evoked potential where Jeff developed a little clamp where it nips the fin, or doesn't nip the fin, it puts some pressure on the fin and simultaneously records on the EEG trace, and also you can then look at the response to that. So we used two of those to within the analysis of the EEG. This is the sort of main pattern of the experiment, and I'll try to just walk you through this. These data here are from 16 tilapia, so not a large number of fish, but as I say, we tried to reduce that. The eye roll reflex involves grabbing the fish and turning it over to see if its eyes try to hold the horizontal plane, and that interfered with the rest of the measurements, so we didn't use that. And all of the parameters were not detectable in all of the fish. So first of all, the fish is anesthetized, then the EEG electrodes are inserted, it's allowed to recover in a recovery tank, then it is stunned, and then it's allowed to recover from that, and eventually on the next slide it is killed by Schedule 1 method, overdose of anesthetic followed by destruction of the brain. So during the initial anesthetic, this is the mean time to loss of these indicators in seconds. They lost the writing reflex first, then movement, and then opercular activity. 1 or 2 fish lost the opercular activity first and then the movement. In the rest of the fish, the sequence was consistent. On recovery, again, these are the average times. The opercular activity came first, movement, then a change in the somatic evoked response. This was, it's kind of complicated. We haven't analysed it fully yet, so it's kind of difficult to explain. Obviously, we didn't see a change here because the electrodes only went in at this point, and then eventually they recovered the writing reflex after just over an average of 200 seconds. Then they were stunned, and then after stunning, we got a return of opercular activity, another change in the somatic evoked response, return of movement, and then the writing reflex. However, one batch of 6 fish didn't recover the writing reflex at all. Exactly the same stun experience, same experimental setup, but none of them recovered the writing reflex. We suspect this may have been associated with the way they were handled prior to coming into the experimental unit, but that hasn't been confirmed yet. During the Schedule 1 killing, the overdose of anaesthetic, we again recorded the loss of the indicators, writing reflex, movement, change in the SER, loss of opercular activity, a change in the visual evoked response, loss of the SER, loss of the VER. This sequence was consistent in all the fish studied, but not all of the indicators were observed in all of the fish. These changes in the VER and the SER are quite complicated, and they're confused by this difficulty of getting accurate placement of the electrodes. And we think part of the problem may be that we're dealing with this situation where you've got a two-dimensional view of a three-dimensional object, and it depends, a small variation of where your perspective is, where the two electrodes are, can affect what you see. So there's considerably more work needs to be done on that. So in case anybody's interested, this is we used 14 fish in the development of the stun parameters for the tilapia, and the field strength that was found to be most effective. You don't want to use stronger field strength because that has both safety and also cost implications. So you're trying to get something that's effective with a minimal field strength. And the one that we've settled on was 10 volts per centimetre in water that was 356 microsiemens per centimetre on average. Duration of 20 seconds of stun, side to side, not head to tail. The duration of apparent unconsciousness was highly variable. As I said before, one batch of 6 fish never recovered the writing reflex, but the average time to recovery of evidence of movement was around 6 minutes. So, back in the real world, most fish are not stunned at all. They're just left to die, probably of asphyxiation. Commercial systems are in use, and the video on the right there shows 2 batches of fish going through the same system. The dark coloured ones have just been partially asphyxiated on ice. The pale coloured ones are ones that have gone through an electrical stunning system. And in reality, how people are evaluating the efficacy of these systems is by just looking for movement. And if I just start that video again, if I can, yeah. What we see here is the ones that have been on ice for a period of time are still flapping around, and the ones that are going through the stunner don't appear to be. So in the perception of the people on the site, the electrical stunning is being effective. Whether these fish are completely unconscious or not is debatable. So, there is no gold standard EEG threshold for consciousness in fish, or arguably in other species, or even in humans. And even if we see a change in the EEG, we don't know how that functionally relates to the perception of noxious stimuli. So, as I said before, what we're trying to do is trying to find something that is more robust than what we have at the moment, which is nothing. The data is still limited, but certainly the loss of the visual evoked response was up to 11 minutes after a clinical opinion would consider the animal to be terminally anaesthetized. And I think this just confirms what people, especially people working at Bristol, have been saying for a long time, which is VR is a good indication you're recording brain activity, but it's far too conservative as an estimate of consciousness. But in the real world, people are still relying, if the fish is moving, it's probably conscious. If it's not, it's probably not. There is this question that originated, well, was reiterated by EFSA, but has been asked by many people, is, are the fish paralyzed or are they unconscious? And we have a bit of a question about this for the audience, which is that with in-water electrical stunning, how would you even manage to paralyze a fish and not render it unconscious? We've looked at the mechanisms. I mean, actually, we can't even come up with a hypothesis about how that would be possible, and that may be the limitation of our understanding. But if anybody could explain how that might be possible, that would be really useful. So thank you very much for your attention, and I don't know if we... I think
Thank you very much, Jimmy. That was fascinating. Does anyone want to answer that question or ask another question? Someone's feeling brave back at the back there.
I'm afraid I am not going to answer this question, Jimmy, but I'm Ben from Tesco. I have a question for you. You inserted the electrodes into the brain and then you applied electric current. Do you think that actually the needles itself, they were obviously conductive? Did that have an impact on the results? Because the current would travel into the brain faster than an animal without electrodes.
Thanks, Ben. So the electrodes don't go into the brain, they go underneath the scales, which is a bit tricky because the scales are very big, hard things. They come underneath the scales, go through the muscle, so that the top of the tilapia head is a dome, but it has 3 ridges coming out along, and then the gaps in between the bony ridges are filled with muscle. So it goes through the muscle and lays alongside the brain, just in contact with the bone, but not into the brain. When in the early stages we were doing some stunning without EEG, and the behavioural responses in those fish was consistent with the ones with the electrodes in. So it's not terribly robust, but we think there's a reasonable indication that the electrodes are not affecting the efficacy of the electrical stun.
Other questions? Well, I had a theoretical one. Even if the fish are paralysed, is that better or worse than not being stunned at all, or not attempting to stun at all? Might being paralysed actually reduce the welfare challenge somewhat?
I think it's certainly not optimal that the animal is paralysed rather than completely unconscious. But there are some kind of other implications of that, which are not direct implications, but lead to kind of human behaviour. So first of all, if you've got bleeding of the animals subsequently, the bleeding is more effective, the animals are not jumping around, so death happens more consistently rather than them being stabbed somewhere else in the body. But there's another thing which Jeff has been talking about for a while, and this is that when these businesses which are processing animals, if they process them like cans of beans, they'll get treated like cans of beans. If you start to make an effort to look after their welfare, and it you know, just purely subjectively, it looks better if they're not jumping around after, you know, when they're being killed. It gives the impression that they matter, and there's a lot of evidence that that actually has a fairly dramatic effect on the way people treat them right throughout the production cycle. So if they're just paralysed, it's certainly not ideal, but it's also not without benefits.
Fascinating, thank you. Other questions out there? Sorry. Yep. Okay. Anyone else got questions then? No? Oh, there's one at the back.
Jimmy, thanks for the great talk. We have got some information on paralysis in fish. I don't have a theoretical explanation, but what we know when electricity is used for electric fishing, when the current is switched off, the fish immediately swims away. When you stun a fish by electricity, there's always an exhaustion phase. So this is what I know of it. So the fact that when the waveform that's being used in electric fishing, and when the current is switched off, the fish immediately swims away, that seems to indicate that in case of electric fishing, the fish is only paralyzed. But I don't have a theoretical explanation for that. That's what I know of it. I hope this is useful information.
Yep, thanks, Hans. And I mean, we've been looking at the mechanisms which underpin that electrofishing. People go along with a net with a couple of electrodes on it and pass an electrical current through the water, and the fish often leap out the water.
What we know of it, if you use only the direct current,
yeah,
you will not induce loss of consciousness. You need an alternating current for that. And in case of electric fishing, they sometimes use only a direct current.
Yeah.
That could, but don't ask me for a theoretical explanation. I don't have it.
I was glad to see you here because it's one of the things I wanted to talk to you about today. But I think that certainly if you imagine you could get paralysis, or there's in the literature there's evidence of paralysis in pigs where the current is passed through the spinal cord rather than through the brain. And there's also case studies in humans where there's been long-term paralysis as a result of current passing through the spinal column rather than through the brain. In the in-water electrical stunning, side-to-side stunning, the water, the field strength is across the brain, and it's difficult to imagine how that interference with the neural structures could happen. And there isn't really evidence of this muscle exhaustion. But Jeff, I don't know if you, wherever you are, I don't know if you've got anything to add to that.
Yes, I think.
You should just get the microphone, Jeff.
I think we routinely expect to see muscle movement quivering in the flanks of the fish after almost any stun. I mean, we know that during the exposure to electricity, the fish are unable to respond. I suppose our question, our interest is what happens afterwards, and I'm not sure whether that's what you were talking about.
Okay, brilliant. Well, thank you for that. Thank you to all our speakers from the last session. That was absolutely fascinating. So, round of applause for all of them. Thank you, Jimmy. It's lunchtime, so if you could be back in here at 1:30, lunch is served out in the library again. Thank you very much, everyone.